Hello. In this video we're going to be talking about Chapter 20, Lecture 21, Learning Objective 1. We're going to look at E-cell under standard conditions, relating it to our delta G under standard conditions and our equilibrium constant. And then we're going to be calculating out our cell potential under non-standard conditions using the Nernst equation. Okay, so the equation we use to relate our cell potential with our free energy is delta G is equal to negative NFE, where N is equal to the number of electrons in the balanced equation, or balanced half reaction. F is Faraday's constant. Which is given as 96,500 coulombs per mole of electrons. And then E cell is our cell potential. Okay, so we can also have standard conditions for this. And in that case, delta G naught is equal to negative NF E naught cell. And keep in mind, if we're under standard conditions, we're at 25 degrees Celsius, 1 atmosphere of pressure or partial pressure, and 1.0 molar for all ion concentrations. Okay. Now, using this equation and combining some equations that we learned from Chapter 19, we can actually convert these into other equations. So from Chapter 19, I want you guys to recall delta G is equal to delta G naught plus RT ln Q. And then the one we just learned, delta G naught is equal to negative NF E naught cell, and delta G is equal to negative NF E cell. So taking this and Faraday's constant, we're going to replace these two pieces of our equation, and we get negative NFE cell is equal to negative NF E naught cell plus RT ln Q, and dividing by negative NF we get E cell is equal to E naught cell minus RT divided by NF ln Q. And then we're going to convert to log and take our temperature at 25 degrees Celsius. And what we get is E cell is equal to E naught cell minus 0.0592 volts divided by N log of Q. So we've just changed it into a log base and put it at 25 degrees Celsius to get this equation. And this is our Nernst equation. As a note, we can further manipulate this equation and take it at equilibrium. At equilibrium, our E cell is equal to 0. So we get log Q, or log K rather, is equal to NE naught cell divided by 0.05 0.592 volts. Okay. So, let's use that and solve for the following problem. So, we want to solve for the potential of a galvanic cell. At 25 degrees Celsius, the galvanic cell is copper solid plus 2 iron 3 plus goes to Cu2 plus 2 Fe2 plus aqueous. So we want to solve for this galvanic cell when our ion concentrations are the following. Fe3 plus is equal to 1.0 times 10 to the negative 4 molar. Cu2 plus is equal to 0.25 molar. And Fe2 plus is equal to 0.20 molar. Okay, so the first thing we need to do is we need to solve for our standard cell potential. So we take and divide this into half reactions. So the oxidation of copper is equal to negative 0.34, the negative of the reduction potential, and then the reduction of our iron 3 plus to iron 2 plus has a reduction potential of 0.77 volts. And we can multiply this by 2 if we so choose in order to get this equation. But it will not make a difference to our E cell, which would be equal to our oxidation potential plus our reduction potential, which gives us a value of 0.43 volts. Okay, so now that we have our E cell, we can further go into this problem by solving for our Q. So our Q here, from our balanced equation, we have our copper 2 plus ions, iron 2 plus squared divided by iron 3 plus squared. So we can then put this into our E cell, our Nernst equation. Our N in this case, if we look for our balanced equation, we know we have to have 2 electrons. So N is equal to 2. And we do our log of 0.25 0.20 squared divided by 1.0 times 10 to the negative 4 squared. And what we get is an E cell equal to 0.25 volts. That is everything for this video. Hope everything made sense, and I see you guys in the next video.